Thank you, Roland, and thank you for allowing me into your show. I'm very pleased to be presenting step 6 of the AI readiness seminars, which follow the ethical AI framework for educators and educational businesses. Sorry, and I'm just trying to, my screen seems to, the slides don't see. I'm just going to stop and go back to.
Okay. I'll do a little skit while you get ready.
Yeah, okay.
A comedy presentation.
Yes, sorry about that. The usual thing, you have somebody who's a professor of AI and he can't work his own laptop. This webinar is for educational businesses, and what we're going to do is explore some of the ways that AI, some of the findings that AI and data can reveal, and also describe some of the leverage that one can make of those findings. We already learned about AI techniques in step 5 a couple of weeks ago from Carmel Kent, and so today we're going to be looking at how we can actually make use of those techniques. And as always, we want you to look at your business and yourself through a data and AI lens so that you can develop an AI mindset. And in order to do that, we need to be very clear about the strengths and weaknesses of AI, artificial intelligence, as opposed to human intelligence. AI is very good at collecting together very large amounts of data, not forgetting it, and also finding patterns in that data which would be very hard to find by a human.
Ben, sorry, Ben, do you just want to share your screen again?
Am I not sharing it?
Yeah, I don't think it's done.
Oh, sorry.
But the intro was very eloquent.
Yeah, well, I've lost the. Oh.
There we go.
Yeah, the trouble was I wasn't able to move forward in my slides when I shared. Okay, actually does not. So, as always, one needs to be thinking about the differences between human intelligence and artificial intelligence. And I've already mentioned a couple of the advantages of artificial intelligence, but humans can see the meaning of data in ways that artificial intelligence can't. They have an understanding of what they know and what they understand in the way that many artificial intelligences don't. And the way forward, we think, is that there's a productive collaboration to be had between humans and machines. And we always think of the AI as being the servant and the human being the master, and the human remaining in the loop. So we're not advocating AI taking over any aspect of education, though it can provide a very useful tool for people in education. So, as Roland said, I'm going to be joined later by Madiha Khan-Galaria, and she is developing tools which can scaffold and assess learning in real-time online environments, and she'll say more about her work later. So who are we? Well, here's the Rogues Gallery. I'm the one on the right there, taken a few years ago, as you can see from the colour of the hair. Anissa Moeni is next door to me. Rose Luckin, our leader, is in the centre. Mutlu Kokorova is next door to her. Mohammed Chowdhury is in the top left corner, Carmel Kent below him, and Ibrahim Bashir at the bottom left-hand corner. So the series of seminars have covered these 7 steps, starting from educating, enthusing, and exciting your educational organization or your business about using AI, through to identifying the kind of data that you might collect, through to applying the techniques that could make use of that data, to the current step 6, which is to understand what the data is telling you about your focus and if necessary, help you return to step 1 until you're AI ready. Earlier this week, Mutlu Kukurova talked about understanding data from the point of view of educationalists. And my job is to give the same kind of talk, but more focused on EdTech businesses than educationists themselves. But clearly there's quite a lot of overlap between these two views of AI readiness. So I'm going to cover 4 topics in terms of the uses of the data. Now, I'm not claiming at all that these are the only 4 uses of data that there are. They're just 4 uses which I think are interesting and which cover quite a lot of the possible space of the use of data. So the first kind of use is undertaking design experiments, trying to try out how your system might work in different versions ahead of actually putting it out there on the large scale. Second is if you see that things aren't quite working as you expected, using data analysis to identify specific issues with the product that need to be fixed. Third is trying to understand what the different parts of your system do in terms of their benefit and educational effectiveness. If you've built a MOOC, for example, do the quizzes have more effect on outcomes than the videos, or what? So that kind of analysis of which bits of the system get used and which bits don't. And then fourthly, trying to understand something about the users and what they pay attention to and how they make use of your system. I'm going to do that within the context of 3 of the main roles for AI and data in education. So the first role, which is exemplified by the picture of the little girl sitting at a laptop, is that AI can act as a teaching assistant to work with an individual child, we see here, or an individual grown-up, come to that, or with a small group. In the bottom left, AI can be used to help a teacher manage a whole class of students. As the numbers go up, the classroom management issue becomes more complicated, and teachers need help with that. And then in the bottom right, AI and data get used to help in understanding what cohorts do or don't do, what they succeed at and what they don't succeed at over years of use of systems. Now I'm going to concentrate on 2 of those areas. I'm going to leave out whole class teacher assistant, not least because Mutlu covered some very nice examples of that in the talk on Tuesday. So I'm going to, the examples I've got in my talk are drawn mostly from individuals and from systems for cohorts. Just to kind of get us started, I like this diagram that comes from the paper by Romero and Ventura, which gives you a sense of the way you can look at education. You can look at it in terms of courses or students or activities and sessions that those students engage in, or within activities and sessions, the actual events and the actual actions that the students actually do. And of course, you can get less data or more data depending on where you look. Near the top of the screen, less data. Near the bottom of the screen, more data. So in events and actions, you might have the click stream of every click, or if you're looking at a cooperative learning in a classroom where students are moving around, video of every learner moving around a classroom and every click on a laptop or an Arduino or whatever it is that they're doing. And the data not only differentiate in terms of the amount of it, but also in the granularity of it. So just looking at how courses get used is quite coarse. Looking at how a particular tool is used in terms of eye gaze or clicks is very fine-grained. So let's start now by looking at some examples of undertaking design experiments as one of the uses of data in AI and education. So this example is an example where it's from a product which is used widely already, and they use the fact that they've got many people using the product to try out new ideas to make the product better. So the product is Duolingo. And I guess many of you have used it at some point or other to learn a foreign language. And it's very popular. It's used across many countries, and it has many languages that it can teach. And their educational, or rather their design philosophy is, quote unquote, test everything. And what they say is, this is one of the key operating principles that we follow at Duolingo in order to continuously improve the learning experience of our users. It means we rely heavily on experiments and data to help us make informed decisions about any updates or new features we launch. So here's an example of the kind of experiment which they do. In this graph, they're looking at how often lessons are completed. Now, what happens with these online systems is that people often start lessons and then abandon them if they don't find them fun, or they don't find them useful, or they don't find them interesting. So they're very much interested in people completing lessons which they've started. So what they wanted to do was to see whether if they added leadership boards, that is those kind of tables of who's done best, which you have in lots of games, if they added a leadership board, would that impact on the lesson completion statistics? So what they did is they set aside some subset of their users. They gave that subset of users a new version of the system which had leadership boards embedded, and then they tracked to see what change was made in the degree to which sessions or lessons were completed. And the graph shows the answer. The blue line shows the many users who use the system without the leadership boards. The green line shows the fewer users in the experiment who did have leadership boards. And you can see a small but significant increase in the way that, in the degree to which people completed their lessons in the case of the leadership boards. So that looked like an experiment that would then be rolled out to all users as a result of that analysis. My second example is from a little way back now, 2005, Methane and Koniga. And I deliberately chose an old example because the issues of doing experiments with data is not particularly new. It's become very fashionable over the last 10 years or so, but it's been going for some time. So Mita and Koniga were working in the context when there were arguments concerning the issue of whether feedback to learners should be immediate or whether it should be delayed in systems that they had developed, which used knowledge components to model the student and model the domain. And what I mean by that is that to build these systems, they did a whole lot of careful analysis of actual learners, and then they tried to break down what you needed to understand into small components so that they could use that with a new learner to see which of those components they had understood and which they had not. And also, they built the system using those components so that it could check against the learner, and also it could do the tasks that it was setting the learner. So the knowledge components were the basic building blocks of a system that could interact with a learner to solve problems. And there was a lot of argument about when things started to go wrong for a learner, whether the feedback should be immediate, saying, sorry, chum, that isn't the way to do it, or whether it should wait and see, and then at the end of the session say, well, you did pretty well up until this point, but then things started to go wrong. Do you want to replay what you did and see and understand how things went wrong? They decided that actually that wasn't a very good question to ask about feedback. It was too crude a question about whether immediate versus delayed. And they came up with a different idea, which was to look at the model of feedback. And they did an experiment which contrasted two different models of giving feedback, one of which they called the intelligent novice model, and the other which they called the expert model. So the expert model on the left here is pretty straightforward. The student reads the problem statement, identifies goals to be accomplished. The student plans actions to accomplish the goals. The student implements the actions. The student attends to feedback. If everything's fine, the student moves on. If wrong, the student is notified of the error, and the student has an option to get instructions to fix the problem. Kind of like absolutely minimal kind of useful feedback. The contrasting intelligent novice model of feedback starts off the same, but then when after the student's implemented actions, things are different. The student attends to outcomes and looks for any discrepancy between the intended result and the actual outcome. If a discrepancy is noted, the student identifies the source of the discrepancy. The student attempts to repair the original solution. If the discrepancy is missed or repair attempt fails, the student is guided through some error detection and correction process. And then you can see that there's a lot more detail in dealing with things not working out as expected compared to the expert model. And then they wanted to see whether, if they had a system with the intelligent novice model, how that compared in terms of its utility and efficiency with a system that had the rather minimal expert model. And they used a technique called learning curves, which are much used in AI in education to track learning data and make decisions about which system is working better. So the way to read this graph is in the vertical, we have the number of attempts required to solve a problem, including a particular knowledge component. The learner might be offered to solve a number of different kinds of problems, but they'll be chosen because they all contain a particular knowledge component that the system wants that learner to learn. So you can see that the scale goes up from 0 to 3, and both learning curves start around 2.5. And what that means is that on average, at the beginning with both systems, the learner has to have about 2.5 opportunities to solve a problem involving a particular knowledge component before they get it right. And along the horizontal are the number of different learning opportunities that they get. So that first one at 2.5 attempts was the first learning opportunity, then the second through to the 6th learning opportunity. And as you'd expect, as you move through the learning opportunities, then the number of attempts to solve a problem containing a particular knowledge component go down because you've learned how to solve the problem. And in terms of answering the question about which system worked better, if you look at the black diamonds, the slope of that curve is downwards, which is good, but not very much. So the students in that system started off needing 2.5 exposures to a problem, to a knowledge component before they solved a problem containing it. And by the end of 6 opportunities, it hardly reached 2 attempts. So a small improvement. By contrast, in the case of the intelligent novice way of providing feedback, this learning curve is quite a lot steeper downwards. So that's a more efficient system because the curve is steeper. Steeper is better. So that was 2 examples of design experiments. Now let's move to identifying specific issues with an educational product. And again, I've got 2 examples. In the first example, fixing in a clear inadequacy in an existing tutor. And then my second example is building tutors with a built-in development path rather than seeing it as an add-on, as an extra for later. So again, I'm going to the work of Koniga and his colleagues with their cognitive tutor for geometry. And they noticed that there was a particular geometry problem that lots of students stumbled over, even though the other problems seemed to go quite well for the students. So they used data mining to look at the data of the problem set and the particular knowledge components that had been stumbled over, and they realized that there were 2 or 3 knowledge components that were poorly expressed and that their relationship hadn't been properly thought through. So what they did was they kept the old system for use as one part of a controlled experiment, but then they updated the domain model of doing these geometry tasks in terms of a better organized set of knowledge components. And then they compared, in a little bit like the way that I've just described, 2 cohorts of students who one had the old system, the other had the new system, and they found that the problem that had caused all the issues in the first place was actually solved much better in the new system, because the new system, in a way, understood the domain of geometry better and therefore understood the students who were trying to learn that domain better too. My second example of improving systems comes from the work of Lewis Johnson. He runs a company called Alelo, and their main product is called N-Skill. And N-Skill is like Duolingo, is a system for learning language. But this system has a few extras. The extras are that you work with the system on a screen. You have an avatar that you interact with. The avatar speaks to you in the language that you wish to learn. You speak back to the avatar in the language you wish to learn. There are also some prompts and other bits of text on the screen that can either be in the target language you're wishing to learn or can be in your own language, so that you can read stuff you can readily understand about your interaction, let's say in Spanish if you're an English speaker. And it's scenario based. So in this scenario, the learner is working with an avatar to buy a train ticket at a railway station. And the system is very nice. It does its job, but as with every system, there are bugs, there are parts of the system that don't work quite as well as they might. There are times when the avatar doesn't quite understand what the learner has said. There are times when learners don't quite understand what the avatar has said, beyond simply the fact that their Spanish say isn't very good. It's because the avatar is not saying something very sensible. And knowing that the system needed to be improved, Johnson said, well, we need to design systems in such a way that we expect to have to debug them as they go. So he built the tools to enable data mining and analysis of how well the system was working into the tool itself, so that he from time to time could develop the system as a result of that data analysis, update the models in the system to work better, redeploy, and so on. He called this the D3 development cycle. So it's a little bit different from the previous example of Koniga, where yes, they found a bug, they delved inside the system and they fixed it, but they did that on, to some extent, an ad hoc basis. What Johnson is doing is trying to reify the upgrade of the system as part of the system design in the first place. So my third example of looking at the ways that data and AI can be used is to try and identify the role of individual components of a product. And I've got one example here, which is analyzing patterns of usage. So I'm referring to the work of Rizvi Rizvi and his colleagues, where they were looking at variation in learning processes in a MOOC provided by FutureLearn. And the context of their analysis was that they made a contrast between two design principles that underlie quite a lot of MOOC development. You can develop a MOOC essentially to maximize retention. You make things easy, you make things enjoyable, and you keep your students through to the end of the MOOC course. And to some extent at odds with that is you can design a MOOC for the depth of learning, which means there are going to be times where things are going to be tricky and hard, in which case you may lose students. So there's a sort of trade-off between retention and depth of learning. It doesn't always have to be like that. It is possible to have deep learning and making it really interesting, but it's harder. So what this particular FutureLearn MOOC did, in a way to try to find a sweet spot between these two, to some extent, contrasting design principles, they asked learners to mark tasks as they were completed. The idea being that if the learner is thinking about, have I completed this task or not, they're also thinking about how much have I got from this task. So the mere fact of marking ought to at least help with the depth of learning without particularly undermining retention. They then did a post-hoc analysis of the way people engaged with that particular MOOC, and they looked at the degree of engagement. And they divided the overall cohort into three groups. The students who marked every task which they actually completed, those who occasionally marked tasks that they completed, the partial markers, and those that never marked tasks, the non-markers. And as you can see from the graphs, where the amount of blue gives you a sense of the amount of stuff that the learners got on with, the markers got on with lots of stuff and were much engaged. The partial markers were less engaged, and the non-markers were minimally engaged. Now, of course, there's a chicken and egg issue here. You can't determine that because of the marking, the markers did more. It's probably more likely that the kinds of students that would do the marking are also the kinds of students that would want to stay engaged. But it's useful to know about whether somebody is marking or not, because in the case of the non-markers, if you spotted non-marking behavior, you could intervene early on and say, look, Fred, I see you're a bit of a non-marker. Do you think that you could start marking, or do you think you would get more out of it if you actually started to think a little bit about the degree of engagement that you're exhibiting on this particular MOOC? But Rizvi also and his colleagues also looked at the different ways that people are paying attention to the MOOC. And they looked at the different kinds of things that were provided in the MOOC. So markers mostly looked at articles, less at discussions, less again at videos, and less again at quizzes. The partial markers had the same pattern as the markers, but with reduced amounts of each of those four different kinds of activity. But interestingly, the non-markers mostly looked at videos, much more than articles, and that more than discussion, and that more than quizzes. So you have a very different pattern of attention, as well as a very different pattern of engagement between markers and non-markers. And I guess one could have predicted that people who weren't paying much attention would probably want to just look at the videos. But this kind of analysis gives you the chance to intervene at an early stage and try to put somebody back on a path which is likely to lead to more engagement and, in fact, more learning from the system. I'm now moving to my last use of data and AI, which is to identify different aspects of users as opposed to components. And I've got two examples again. looking at the relationship of the assessments that you set to the engagement of your students, and also looking at the analysis of the regularity of the interaction, not just the amount of interaction. So Rientes and his colleagues looked at 3 case studies of interventions on open learning systems at the Open University. And they contrasted an arts module, a psychology module, and a technology module. And I'm not going to go into any particular depth about the contrast, but I just wanted to show you these graphs, and I've just taken one now for the psychology module to show how these kinds of really quite simple graphs tell you quite a lot. So this graph runs over a calendar year, sorry, an academic year. The blue line shows the total number of students who are still taking part in the course. So as you can see, it does slope downwards, but not dramatically downwards. So retention was good. The orangey, ochre, yellow line is the line of the degree of engagement that students are showing. So what you can see is in the early days, the first few weeks of the course, engagement goes up, then it dips a bit, and then it goes up again till it, and at the point where it reaches a little peak, we have an assignment. And then what happens after the assignment, engagements decreases again, and then it increases again just before the next assignment. So there's a very clear, neat relationship between when you set the assignments and when you get the maximum engagement. So this allows people who design these kinds of courses to really think about the timing of any assessments or assignments that they give in terms of trying to maximize engagement overall. And my second example of looking at learner behavior is from Peach and his colleagues' work, recent again, and they looked at 2 online systems, one in the business school at Imperial College and another at the Open University. And what they were concerned with was task completion, timing, the regularity of interactions with the learning system. And they produced wonderfully complicated graphs like this. I'm not going to explain it all, but I do want to explain a bit about it. So if you pay attention to the area up here, what we see is a graph of time in months against tasks. So the tasks are numbered from task 0 at the beginning of the course, or maybe task 1 at the beginning of the course, up to task 990 something at the end of the course. And the timing is shown, the black line here shows the average of when people paid attention to that task. So if there's a bit of a long line here, it means that people spent quite a lot of time on that particular task. Where there's not much of a line, they did the task quickly. So people on this task, let's call it task number 300, people spent from something like the 2nd month up until the 6th month working on that task. So the average of all of the students is the black line. But there were some students who, the green line, who always were a little bit below the black line, i.e. they were what Peach and his colleagues called the early birds. They got things done largely ahead of all the others. You've then got people down here in the bottom corner who they called the crammers, because they tend to be behind. If you think, remember that time is going upwards here, they are behind the average all of the time. I think we've all met crammers in our lives as teachers. And then there were other kinds. There were people who were always pretty much the average on time. There were the low engagers who did rather less. And then there were a couple of outliers. So what did they learn from this? Well, as one would expect, the poor performers typically evidenced cramming behavior. No surprise there. But what I found an interesting result was that the good performers, i.e. the people who did well at the end, were found in all of the time-related groupings. So some good performers were early birds, some good performers were crammers, some were sporadic, and some were average. So that for me was an interesting result that I hadn't expected, though I had expected the poor performers to cluster amongst the crammers. I want to finish with a cautionary tale about data. There's a very interesting paper by Alexandron and his colleagues about fake learners. It turns out that learners have found out how to game the system in some MOOCs. And the way that they game the system is that a learner who wishes to game the system sets up 2 accounts in the same MOOC. In one account, called Alexandron calls the harvester account, the learner plays dumb and pretends, well, maybe doesn't even pretend, doesn't get anything correct. And the system offers prompts and help and eventually helps the learner get to the right answer. In the other account called the master, the learner apparently, now knowing the answer, gets everything right. So the master account gets the certificate from the MOOC provider saying you did brilliantly well. And of course, he can then flash that certificate to whoever he wishes or she wishes to show it. The harvester doesn't get the certificate. But of course, if you're looking at data from such a MOOC, you have to be aware that in some cases, not in every case, that there are going to be 2 students, there are going to be, 2 accounts for each student. And your analysis of engagement, for example, is going to be skewed because it may look like that the harvester is more engaged, but the master is less engaged because the master learned the answers from the harvester. Alexandron gives us a percentage of around 13% in one analysis for the number of students who play this kind of gaming. So let me just give a brief summary of what I've tried to do. I've tried to give some examples, not the whole story, but just some examples of the way that you can use data and AI as part of building tools, designing tools, debugging tools, finding out how your tools are used. I gave some examples of undertaking design experiments, Duolingo being a very contemporary example of that. I gave some examples of identifying specific issues with an educational product. And I think Lewis Johnson's D3 development cycle built into the tool itself allows for debugging as you go. I gave an example of understanding about how individual components of a system get used. You remember the markers versus the non-markers, and the fact that the non-markers use video much more than articles, and the markers looked at articles much more than video. And I looked at examples of getting to understand users. In the last example, contrasting the crammers with the early birds. And of course, there is some overlap between identifying individual components of a system and identifying aspects of users, because in a way, it's the cross product of users and components that one is often interested in. And I gave one cautionary tale about the analysis of data. And the cautionary tale is to provide a little bit of flesh on a point that was made all through these seminars, that you have to undertake your activities in an ethical way. And looking at data and looking at its uses, to do that ethically, you have to be aware where the data may be misleading and try to allow for that. So I think that's now enough for me, and it's time to allow some questions. So I'm going to hand back to Roland.
Hi Ben. I just wonder if we, as we've only got about 20 minutes left, if we should have Madiha's contribution first, and then we'll ask the.
I'm very happy. I'm very happy with that.
Yeah. Madiha, are you okay to share your screen in a second?
Yeah, I'll just do that now.
Great.
Okay, you should be able to see it.
Yeah, yeah.
Yeah, all right.
I think that's the presenter. Oh no, you haven't actually enlarged it yet. Press play. Yeah.
The presentation view.
Wonderful.
There we go. Yes.
Super.
Okay, brilliant. So hi everyone. I'm Madiha, and I'm doing a PhD at the Knowledge Lab. I'm doing it with Third Space Learning, which is an online tutoring company. They have one-to-one tuition for upper primary school children, and they use human tutors. They're keen to make use of their data to create intelligent tools to support either the learners or the tutors. And that's where I've become involved. My background is in strategy consulting, so it's quite interesting actually to be doing this PhD and to be looking at it from a very much an exploratory research point of view, but with a view to it being potentially operationalized at a later date. So in terms of the scope of the work that we're doing, we're working on self-regulated learning, and in particular, we're looking at how we can use learning analytics to support tutors as they scaffold learners with their self-regulation. So self-regulation is, in our study, interpreted as a social construct. So the idea is that tutors can promote learner self-regulation, for example, through metacognitive prompts or through encouraging constructive open-ended dialogue with students, encouraging them to take more control over their own learning. The hope is that we'll be able to use this data to be able to come up with a clear idea of how tutors can support learner self-regulated learning within the context of an online tutoring environment, and what success looks like. This in itself is an area which needs a significant amount of research. And then secondly, we'd like to understand how can we use the data that Third Space Learning is collecting to identify these patterns of behavior and support the development of intelligent tools. So there are 3 steps to the work that we're doing. The first is developing a framework. The second is validating that framework based on observations of learners and tutor questionnaires. And then finally, coding that data based on our framework and analyzing it through sequential mining, for example, process mining and decision trees, and then doing this entire process in a very iterative manner. So once we have the first batch of results come back, then redeveloping the framework and launching it again. We've developed the framework on the basis of the Winian-Hadwin theory. So the idea is very much to contextualize established educational theory to this online tutoring environment, and build the framework of signifiers on that basis, so it's theoretically sound. The Winian-Hadwin model is here in this page. It's a complex model, and I'm not going to go through all of it at the moment because time would not allow for that. However, what we will do is we will look at the tutor behavior from within conditions. So tutors are an external regulatory force on learner self-regulation. And then if you can see the operations bit of the model, that's the learner self-regulated behavior, which is being affected by the tutor. This slide here shows the framework of signifiers from the tutor perspective. So, for example, some of the practices that we've identified as being relevant to the promotion of learner self-regulation are things such as boosting learner affect and motivation. There are various types of traces that we can use to identify when this has happened. So there's a natural dialogue between the tutor and the student. So praise would be one. In addition to that, there are also non-audio traces. So the platform allows for tutors to give effort points, pictures, stickers, drawings, and all of those are done with a view to maintaining tutor-learner engagement. So they act as non-audio traces there. We also have various forms of engagement here. So we have directive engagement, explanatory, guided, and those all refer to, again, the amount of control that the tutor is keeping over the process versus the learner. The framework of learner signifiers here on this slide shows the learner operations that are identified by the Winian-Hadwin model. So searching, monitoring, assembling, rehearsing, and translating. And again, we have the audio traces and the non-audio traces here. Early stage analysis shows some very interesting differences between the various groups of tutors. So at the moment, we are looking at clusters of tutors based on the classifications by third space learning. And we're looking at the differences on that basis. That in itself is an area for research, as this may be the ground truth as TSL sees it, but it's not necessarily the representation of reality. So we will be looking at different ways to possibly classify these tutors, for example, through learner outcomes. What we have found is that based on this clustering, the higher ranking tutors show paths where the use of effort points and praise is a very integral part of the session, and it's well integrated into the flow of the session, indicating that these tutors are very adept at using the resources at their disposal. While, for example, for low-ranking tutors, they tend to rely on much more directive engagement and are not as comfortable with collaborative engagement with the learner. In terms of the next steps, so the analysis that we're doing is process mining and other forms of sequential mining. We will use this to identify nodes for a decision tree and use that to classify tutors by performance. We hope to be able to build tools which will scaffold, for example, the tutors. So it could detect when the tutor is engaging in a maladaptive pattern of behavior and prompt the tutor away from this in real time. And the other option for, further down the line would be, for example, something like training and evaluation. So could be used with analytics to identify which tutors are performing well and which are in need of additional training. So that's it from me, but I'd be happy to answer any questions.
Thanks very much, Madiha. That's wonderful.
Yeah, thank you, Madiha.
No problem.
So, Ben, did you want to say anything, or I do have a couple of questions.
I just wanted to thank Madiha for a really interesting example of project. I see we've got potentially some questions, Roland. I have a question for Madiha, but I'll let the audience ask their questions first.
Okay, sure. So somebody's come to me with a question that we found quite interesting. I was thinking this when I was looking at the slides earlier as well, about the Johnson's D3 model, the kind of where it was basically conducting the data mining, and then it would sort of integrate discover the bugs, and then that would be part of the process for the development of the product itself. And we were just wondering if such a sort of model could be extended for the platform itself to sort of recalibrate. Could a platform itself be produced that would correct itself, rather than having the sort of the bugs found, and would that framework be used to support a learner rather than to just discover the bugs? Could it sort of recalibrate itself to better teach the learner?
Okay, I've got 2 points to make in relation to that. The D3 model has a certain amount of human intervention. It's not completely automatic. So it's kind of based on the idea that the system will will create a detailed log file of every interaction, and there'll be a number of data analytic tools which are designed to work on those log files and allow the designers then to spot the expected kinds of signatures of where things aren't working as they should. But in terms of the more interesting question, half of your question, which is about, could you imagine a system that could learn how to get better at teaching itself. That has been a goal in AI and Ed for a long time. One of the very earliest papers in AI and Ed was called A Self-Improving Tutor for Arithmetic by Tim O'Shea, formerly principal at Edinburgh University. And he built a system that had a kind of theory of education. It had a theory of doing experiments. It would, a little bit like Duolingo, it would set up an experiment based on a theory of what might make things better for the student, try out the experiment, look at the results, and if the results showed that what had been suggested could be improved, then employ that improvement. So yes, people have tried that, and there are some more intermediate examples too, but it's very difficult because the human in the loop can decide issues around what kind of an experiment should we try, what would be a plausible experiment, and that's quite hard unless you have a theory of the space of possible experiments to try.
Thanks, Ben. So we got a question that Mutlu's put out to the group, just asking, what is the particular advantage or value of AI in Ed in contrast to more traditional data analysis techniques that were presented in some of the examples that we looked at? Why do we bother with AI and what can it do that we wouldn't be able to do with the data science and other sort of modeling that we've already got?
Well, it's a very good question because AI is kind of turned into a brand. And you need to say that your system has got more AI in it than some other system in order to sell it. The fact that actually it may be, traditional statistical techniques is neither here nor there. So there's a sort of gray area between traditional stats and AI, which is glossed over because AI sounds sexier than regression analysis. So there are places where AI will work. I mean, if you take the big classic recent ways that AI has been used, let's say in medicine or in game playing, where the system learns from masses of amounts of data which is ill-structured, you can't use traditional statistical techniques in those cases. So there are situations where you need AI to be able to discover the patterns in the data where traditional stats can't do it. But there are going to be plenty of cases where it's a gray area and it'll be a matter of convenience and efficiency between whether you use a traditional statistical technique to find a pattern or whether you use an AI one. But for many companies, they're probably going to label it as an AI, irrespective of whether it's an AI or not.
I wonder, Madiha, do you have a thought on that as well yourself, or?
Yeah, I think I agree with a lot of what Ben just said right now. I think it is, people want to hear the word AI, even when it's data science or actually something more traditionally in terms of statistics. It is a much more of a sexier tool, and it's something which, especially from an investor point of view, they understand straight away without, even though it's a black box, but everyone kind of knows what AI represents and how it's going to create efficiencies straight away. Because data science and all the various traditional analytical techniques that can create the same efficiencies just haven't been in the press as much and haven't created that same buzz around them. They're not used in the same way. And I think businesses do find that they can interchangeably use AI versus data science, and so they wind up doing that. They wind up just looking at it in as one big piece rather than two separate things.
I've got another question here regarding the section that we looked at earlier about the marking. So the learners being prompted to mark their own work. Someone's asked, would it be the role of the system, or perhaps, you know, is it ideally the role of the system or of the human instructor to sort of go and give the student feedback when you're looking at the sort of the marker, non-marker divide? Like, you know, is it better for a human to prompt the non-marker to start marking in order to boost their engagement, or should we get the system to do it?
That's an interesting question, and I don't know that there's a definitive answer to it. I know where I suspect the answer is, which is that the system will be good at spotting a pattern in a learner behavior, especially if there are a lot of learners, and alerting a human teacher. And it may be that the human teacher is in a better position to try to get the student to be a little bit more enthusiastic about what they're being exposed to in terms of the MOOC or whatever learning system it is. I mean, on the whole, most educational technologies assume either that the learner wants to use them anyway, or that if they don't, it's down to the teacher to kind of explain why it's good for the learner to use the system, what they're going to get out of it, why they'll be a better person by the end of it than they were at the start, because people are better at being able to situate the learner better in the context of the learning they're trying to do, because they can understand why this slightly disgruntled adolescent who is sitting at the geometry tutor and wondering why he should learn Pythagoras, they might well have an answer to that question, which actually makes sense to that student in a way that the system itself is very unlikely to be able to do. So I like the idea of, yeah, the system can spot the behavior, but the human can do the best to repair it.
Just muted myself. Your thoughts on that?
Is that for me?
Yes.
Yeah. So I would especially with the research that we're doing. I mean, we're working with upper primary school children. So with this category, it's very important that the tools are, in order for them to be effective. There's a case for saying, well, do you play it back to the learner? But in that case, a lot of research needs to be done to understand how you can actually make it engaging for the learner and trigger some type of a reaction from the learner. The slightly more straightforward thing to do at this point is to be instructor facing and get the instructor to see the behavior and then work in dealing with that behavior. So yeah, I think there's a big case for systems that face instructors and work in collaboration with those instructors.
Brilliant. All right. Thank you very much. We've sort of come to the end of the session now. So I just wanted to say a big thank you to Madiha Khan and to Benedict du Boulay. I've posted in the chat a couple of links to their work as well, so you can see a bit more about each of their individual fields of research and what they're working on currently. And I just want to say thank you to the audience for coming along as well. And I've set up I've put in a reminder in the chat as well, just to let you know that our next set of webinars will be taking place at the beginning of September. So we're taking a bit of a break for August, as we presume the majority of you will also be taking a break during August. So yeah, the events are live on Eventbrite. Please feel free to sign up. We'll be tweeting about it, putting it on social media, and I'll be advertising the recording of this webinar as well on social media. So again, just wanted to thank everybody and hope you have a lovely afternoon. And it's going to be 33 degrees tomorrow in London, so hopefully you can get some sunbathing done. Yeah. And take care, everybody. Thanks for coming along.
Thank you, Roland. Thank you, Madiha.
Thanks, Roland. Thank you, guys. Thank you. Bye.